with SPIRou at CHFT, near-infrared radio velocities and spectropolarimetry. Pascal, the floor is yours.
Thank you, Francesco. So good morning, and thank you to the organizer for inviting me to present the wonderful instrument that is SPIRou. So first, I would like to introduce the SPIRou team. So the PI and the conceptor of the instrument is Jean-François Donati from the Toulouse University in France. Co-PI is in this room, René Doyon from the Montreal University. And there were more than 100 people involved in the construction, tests, and science capabilities of this instrument from several countries. So the spectrometer is located at CHFT on the beautiful island of Hawaii. And it's a 3.6 meter telescope. We use the Cassegrain focus at an f/8 ratio. There are 5 instruments on this telescope, so we have to share the telescope time. And unfortunately, as it was said by Andreas previously, we have to use only the bright time. So it makes some problems with, for example, aliases in the periodograms around the moon cycle. So we have 3 parts of this spectrometer. There is the Cassegrain unit, which is attached to the telescope, and that contains the polarimeter and the fiber injection. Then we have 40-meter fibers going down to a room where the spectrograph is. So it is a cryogenic spectrograph, which is stabilized in temperature at better than 1 millikelvin and 10 to the -6 millibar pressure. The wavelength range is quite large. It goes from 0.95 micron to 2.5 micron, but the resolution is good, 70,000. And we use an H4RG detector with 15 micron pixel, so slightly different from the version of the Roman telescope. Here is a scheme of the instrument. So we start from the slit. The slit, in fact, is a pupil slicer, and we have 3 fibers on the detectors. It goes to the parabola, then it goes through the cross disperser with 3 prisms, goes to the echelle grating, back to the cross disperser so that we have the orders that are well on the detectors and with almost constant separation. Then back to the parabola, fold mirror, then back to the parabola, and then we go through the camera to the detector. So the third unit is an important one, the calibration and radial velocity reference unit. So we have a white lamp for the flat fields that is used for the location of the orders on the detectors. Then we have a hollow cathode, which uses mainly the uranium lines for wavelength calibration and gives an absolute calibration at the level of 3 to 4 meters per second. We have a SPIRou at the same time as we observe the stars, so we can monitor the drift of the spectrometer during the night. And it has a relative calibration with a precision of 10 to 20 centimeters per second. And then we also have a laser frequency comb from the Menlo company, and it has about the same precision as the SPIRou, but with slightly different things. So it's very interesting to compare what gives the LFC and the SPIRou. But it is a proprietary LFC, so until now we have not used it a lot, but we plan to do it in the future to improve the calibration. So the first light was in April 2018, and we used the well-known AD Leo star for this. So here you can see the 3 fibers in a row. So from left to right, you have all the orders, and within one order, you have the 3 fibers. So on the right, you have the calibration fiber with the SPIRou. Then we move from a 2D spectrum to a 1D spectrum. And you can see there the telluric lines, which are pretty prominent. And then we correct for the tellurics. So on the bottom part, you can see in red with the tellurics. The tellurics themselves are in green. And when we correct, you get the spectrum in yellow. So after the first light, we had about 40 nights of commissioning and science verification of the instrument, which lasted about 1 year. And then we started the SPIRou legacy survey, which was allocated 310 nights between 2019 and 2022. Of them, we observed 234, so that's 75% rate of observation, which is quite good. And we have 3 main science drivers. So work package 1 about finding new planets, work package 2 about follow-up of transits, and work package 3, which is using the polarimetric capability of the instrument to study the magnetic pre-main sequence stars. We have an SLS executive board with about 10 people that is organizing a weekly telecon of each work package and administrating the survey. So obviously, no instrument is useful if you don't have a good pipeline for reducing the data. So here we have this EPRV data reduction software designed by the people who are mentioned here, but mainly 2 people who are here in the room, Neil Cook and Etienne Artigot. So you can discuss with them about details. The data are implemented on 4 different sites. So we have the CADC, which gets the data reduced at CHFT. We have 1 site in Montreal, 1 in France in Marseille, and a new one in Toulouse. And then after the EPRV, we have additional codes for example, to get a precision radial velocity, we have this line-by-line method, and we have codes for the polarimetry analysis. We have also another reduction software designed by the PI, which is called LibreSprit, and which is a legacy of what was implemented in the visible on Espadon at CHFT. And the code is well maintained, and the documentation is very good, and it is well commented. So thanks to Neil Cook. And so I invite you to discuss with him about the details of the corrections, and because I cannot enter this right now. So the SPIRou performances on an M dwarf with a magnitude in H of 11, you get a signal to noise ratio of about 100 in 1 hour. The thermal background at 2.35 micron is equivalent to a H magnitude of 9 star. The relative radial velocity stability that you get with the SPIRou is between 10 and 20 centimeters over 30 hours. And the RV precision is about 2 meters per second over 3 years for a signal to noise ratio of 150. For the polarimetry, we use 4 sub-exposure where we move rhombs so that we can get a different polarimetric state. And we study mainly the circular polarization, and we have a good linear to circular crosstalk less than 1%. So the velocimetry, so obviously what you see in the infrared is different from what you see in the visible if you have active stars. So here the example is given on AD Leo. So the red points correspond to SPIRou, and the blue points correspond to the SOPHY spectrometer at OHP in France. So generally, SOPHY is able to reach 1 to 2 meters per second precision. But in that case, you see that you have an amplitude of about 25 meters per second. And when you go to the infrared, you have something which is much more stable at the 2 or 3 meters per second stability. And we were able with that to not confirm the planet that was claimed at the same rotation period as the rotation of the star, because clearly you don't see this variation. Thank you. You don't see this variation in the infrared. So clearly the message is that for active stars, you should use near infrared and spectropolarimetry. On the left plot, you can see for the different photometric bands, the Y, J, H, K, what is the precision. So clearly in H, it's the best that we can do. We have been doing stellar characterization by comparing our high resolution spectra with model atmospheres. So the message is that from one model atmosphere like Mars to Phoenix, there are differences. None of the two is reproducing all the lines that we can observe with SPIRou. So it's a little bit challenging, but as you can see on the plots here, compared to the Man et al. 2015 publication, we get a good estimate of temperature, metallicity, and a little bit less about the gravity. And we are now working on the effect of the magnetic field for those stars. We can also measure the stellar rotation periods using the circular polarization. So we use the Stokes VNI and we measure the longitudinal magnetic field. And we see here the variation as they are not periodic, but quasi-periodic. We use Gaussian process to model them. And we were able to measure a large fraction of our M dwarfs. We measured the rotation period. We also characterize the transiting planets. So we do RV follow-up, but also transmission spectroscopy. And here I give 3 examples of discoveries where the mass of the planet was planet or companion was measured. We also do the magnetic stars from the Primoine sequence. So here is an example with AUMIC. So you have a variation with an amplitude of 45 meters per second. And when you filter, when you model the activity and you filter it, you are able to see a planet with a signal of 8 meters per second. And there are more planets that have been discovered by other teams and that we can discover from the SPIRou data. So in conclusion, SPIRou is a precise velocimeter, but it has also advantages because it's in the near infrared, so it mitigates the activity. The spectropolarimetry allows the characterization of this activity. We have already more than 30 papers published, and there is 1 new paper every month right now. And we have more planet discoveries coming and also more planet refutations. Thank you very much.
Thank you, Pascal. And there is time for 1 or 2 questions. I have one in the meantime, maybe. Yeah. You mentioned the calibration accuracy with the uranium neon of 3 to 4 meters per second. Is this the limitation?
No, because we use we calibrate the uranium neon with the SPIRou. So we use both at the same time and we improve the precision. So we get this relative precision of 20 centimeters per second. And with the LFC, this is an absolute precision. So,
but you do not yet use the LFC, correct?
We use the LFC, so we observed all the SLS with the LFC, but we are currently analyzing the data. So okay. It is not involved in the publication right now.
Okay. There is.
Thank you for the great talk. Do you see a path to getting better M/H measurements than the Man et al? Because the error bars you were showing were similar, but the high resolution spectra in principle should do much better, right?
So you mean the error bars of the metallicity measurements?
Yeah.
Why should they be better?
Well, because you're comparing with the Man calibration, which is just a photometric and Gaia parallax calibration, right? And you have high resolution spectra here.
Yeah, so basically the problem is that the models do not reproduce all the lines. When they reproduce the lines, they are wider, for example, than what we observe. So from one model to the other, we made some tests. For example, we injected Phoenix models and we analyzed with the Marx model atmosphere, and we got different values. And then we did the reverse. So I think that this is the main limitation. The model atmospheres are not good enough to reproduce what we see in the reality with the high resolution spectrometers.
Great. Thank you.
Okay, let's